Okay, welcome back everybody. So we're heading into Lab 5, confidence intervals. I'm just going to jump into number 1 here with you. We want to generate, I think that number 1 on this lab is the most complicated of them all, so I want to help you with that. Generate 50 random samples of n equals 30 from a normal population with mu equal to 69 and sigma equal to 3. Construct 90% confidence intervals for each of the 50 samples. These confidence intervals will appear in our output window, and we can copy paste them into the spreadsheet, as you'll see I'm going to do here in a moment. There's various ways you can do this. I'm going to try and take you the easiest path. So what I said to you in class was that a 90% confidence interval means that of 100 similarly constructed intervals, we would expect 90 out of 100 of them to contain the true population parameter, which from a scientific perspective, how often do you really know mu? Okay? Usually the population parameter of interest is unbeknownst to you. So I go out and gather a sample, you go out and gather a sample, we all go out and gather 100 different samples. Well, with a 90% confidence interval, we would expect that 90 out of 100 of our samples to contain the true population parameter. But the thing is, we're not generating 100. We're going to generate 50. So let me see if I can get you to say this. All right, well, what's 90% of 50 then? Okay, 45. So when we do this simulation, we would actually expect that 45 out of 50 similarly constructed intervals would contain the true population parameter. So, all right, let's go for it. Okay, so here we are back at Megastat. So what I initially did, I was playing around with this myself, looking for the easiest way to possibly do this lab. So I remembered we can generate random numbers with Megastat very easily, so we go to that. Okay, we want 30, sample of size 30, so 30 is our little n, coming from a normal, so click on the word normal here, normal population with a mean of 69 and a standard deviation, let me see, what did we say it was, 3. So with a standard deviation of 3. So like I said, it's kind of like as a scientist, you don't know the true population mean or the true population standard deviation, but you're using your sample as evidence to say something about the true population, where it resides within such and such a bounds. That's the notion of a confidence interval. So, and what we know about level of confidence after we'll see with this experiment, we don't need to repeat an experiment over and over and over again to have some faith that these levels of confidence are true. Okay? Hit OK. And what I did was I saw, oh great, it puts it out here on our output session, but then I thought, let me see if I can highlight the first number and see the command up here, normal inverse. So what I did is say, let me steal this command, Control C, copy paste, right? Go into a new sheet, and actually let's erase that. Go into a new sheet and paste in that command. But see, the thing is, we don't want it to say this B4, B5. If I put my cursor here, notice it tells you how it wants it. It wants the mean, comma, the standard deviation. Well, we know the mean is 69 and the standard deviation is 3. So I'm just going to kind of writing my own command based off of what I saw there. Okay, now I'll hit enter. Now what it does is it randomly generated a pick, basically, from a population. You say, well, that's just one little pick, and we need a sample of size 30. Okay, so here's one sample of size 30. Notice I'm doing the click and drag. See? Now if I were to get the mean of this one little bitty sample here, I bet you it would be awfully close to 69 since we were sampling from a population of that. But remember, we want to repeat that 50 times. So, I'm sure by now you know a lot about click and drag. So if we highlight here, go all the way over, and say we just go over this far to T. Well, there's 26 letters in the alphabet, and we have to repeat this experiment 50 times eventually. So, but we can drag this all the way down to 30. And I'll let you do it further on your actual experiment. I'm just kind of giving you the gist here. Okay? So now what I've done is repeated this experiment many, many times. Okay? You have to do it 50 times. But these act as, 20-some different samples, all with their own sample mean and all with their own confidence interval, as we're going to see here in a moment. So let's actually go back to the Word document temporarily. Okay. So let's see if it'll let me write on here. Oops. Okay, so I wanted to remind you that our end game with this is, we're going to construct 90% confidence intervals for each of our 50 samples. And then eventually you're going to look at your confidence intervals and say, okay, how many of the intervals failed to correctly estimate mu? Highlight those intervals on your printout, meaning how many of your intervals didn't have the true mu equals 69 within that interval, and how many did. Well, like I said, if you're at 90% confidence, you would expect theoretically that about 45 of them would contain the true mu and that 5 of them would not. But we're running a simulation, so we'll see how close that gets. And then of course what percent of your intervals contain mu, and I'll let you kind of go through the language there. I just want to show you the mechanics of it all. Okay, now I want to show you what I initially did, because I hope you don't go down this same path. I went to Megastat and I thought, confidence intervals. But the way Megastat wants it is it wants you to tell it, the sample mean and the sample standard deviation, and it'll construct one confidence interval based off of your one sample. But that's not what we want. We wish that Megastat had a way of getting, I don't want to do it one by one for every single little sample. So here's something cool that I found. You can go to Megastat, Descriptive Statistics. This is going to make your life so much easier. Notice confidence interval is under here. And notice those defaults, 99, 95, and 90. So we'll go with 90 for starters. Okay? And then input range. Remember, it gives you that option to input range. So you can actually highlight, let me go back to the top of the table. You can actually highlight all of your data. So when you have all 50 of your samples in there, wait till you see the output on this. Oops, I should have went this way. So yeah, just highlight all of your data. Okay, and then go back to here, and then just hit OK. And look at that. Look at how it shows you. Okay, you had 20 samples. Now remember, for you need 50 samples. I just did it a little bit. And it tells you, the sample size, and it tells you the interval for each one. So let me kind of zoom in here. It'll let me. So basically, for my first sample, I see my confidence interval is, basically from 68 to 70.1. So, does 69 live within that interval? Yes. My next confidence interval was, 68 to 70.5. So, does the true parameter live within that interval? Yes. So I just can very quickly scan through and say, okay, how many of these intervals, actually contained the true population parameter? And so far, just the first 8, they all did. But you'd have to go through all 50 of them. Okay? So I'll let you go through, all 50 of your samples and tally up how many of them failed to contain the true population parameter and how many of them actually did. So I'm moving back to this Word document again. So it said, Part D, I'm just scooting down to Part D. It said, based on your confidence level using this example, what percent of the intervals did you expect to contain mu based off of the confidence level? And we basically said we expected 90% of them to. And then you compare your actual to your simulation, your theoretical to your experimental. Okay. Then I really wanted to jump to Part F here. Calculate 5 95% confidence intervals and calculate the width of each interval. And you know how to do that now, so let me just see what we're getting at. For the first 5 of your 90% confidence intervals that you just created, calculate the width of those intervals, and what do you discover? And we want you to round to the nearest hundredth. So let's just take a look. And it says how to do it by subtracting the lower limit from the upper limit. Okay, so if you look on here, I'm just going to grab the first one. The width of the interval, well, you can do it a couple ways. The computer's nice and gives you the half width, so you could just take the half width and multiply it by 2. That's a different way. So 1.032134, if I just multiply that by 2, and the width of my confidence interval then is 2.06, rounded to the nearest hundredth. So the width of my first interval is 2.06, rounded. And then I'll do that for the second interval. Well, you can kind of see if I take take your half width, basically, and multiply it by 2, okay? And really what we're trying to get is a comparison. Is the width of the interval higher for a 90% confidence interval, or is it lower? Width is another way of saying, half width is another way of saying margin of error. So it's a sort of hidden way to get you to talk about the margin of error. But is the width of the interval larger or smaller for the 90% versus the 95%? That's the gist. I don't want to give away all the answers. So that's what you could do there. So you can compare your first 5, basically, for your 90% to your first 5 of the 95%, just to get a feel for that. Like I said, you can copy-paste all that calculation or information into your document. Okay, so now I'm ready to help you out with number 2. For this example, you're going to enter your data into your spreadsheet, and what we're looking at is the resting heart rates for 20 male athletes between ages 18 to 25. So we have the heart rates listed. I just put them into my spreadsheet, type them in. You can copy-paste and then type them in if you want. You're interested in knowing a confidence interval for mu, the average resting heart rate of all, keyword all, male athletes of this age group. What assumptions are needed in order to use T procedures? So list all the assumptions that are in our text. And again, I don't want to give away all the answers, so I'll let you play with that. Are they met? Include a histogram and a box plot of the data. And then we'll just go ahead and construct our 99% confidence interval for mu and interpret. Okay, let's take a look. So I have the data here. It's been a while since we've done histograms and box plots. So we'll go to descriptive statistics, and I'm going to take away that thing and just look for the box plot temporarily. Input range, so we'll highlight our data set, and we'll hit OK. So we have a box plot, and we see the box isn't like shifted severely left or severely right, and we also don't see any outliers. So no heavy skew, no outliers. That's good, looking good for T procedures. Okay. We might as well couple, oops, I'm on sheet 2. We might as well couple a histogram with that. So frequency distribution, quantitative. Remember, anything important, cut and paste it into your Word document. I'm just going through the mechanics with you. Input range. Highlight. Okay, go ahead and hit OK. Ignore the error message. It's just a software glitch. I'll move that over. So you have your histogram. And we see, I'm just going to highlight on here, fairly normal. No heavy skew, meaning my histogram, doesn't look like that, which would be severely skewed. Okay. So again, these assumptions to use T procedures are looking pretty good. There is one other assumption that was listed in the textbook, something about I'll give you a hint, sample size with relation to the population size. Okay. All right, but now we're ready. Let's go ahead and construct an interval. So add-ins, megastat, confidence interval. We'll click, see it says Z or T. Well, we don't know the true population mean, and we don't know the population standard deviation either, which one normally doesn't. That's why we're running a t-interval. Okay. So when it asks for mean and standard deviation of my sample, if I happen to have retrieved my sample mean and standard dev, that's one way of getting it, and then I could tell it the 99% confidence interval. But since I haven't computed that yet, I think we're going to kind of cheat and go the way we went earlier. Let's go back to descriptives, take off box plot. Let's just put the mean, the sample standard dev. And you know what? I love that it has it with here along with it. You can do your 99% confidence interval. Okay? But here, it doesn't, I'm going to assume it's using a t. I'll double check that in a moment. I'm assuming it's using a t interval, but I'll double check that. Hit OK. I'm going to scoot this stuff to the side. So it gives me this confidence interval here, but it didn't give me the option of choosing a z or a t. So, and my sample size is small. It's less than 30. So to be safe, I'm going to copy down the mean here, which is 59.55. I'm just going to, basically I'm just going to paste this information into my sheet so I have it in front of me. There it is. Okay, now I'm going to go back. So now I'm going to go back to Megastat and be safe about, selecting t intervals. So confidence intervals, see I have it on t. The mean now I is the sample mean, so 59.55. It's much like using your TI-83, it's just kind of looking at it in a different way. Sample standard dev is 4.26. Confidence level 99. Sample size we said was 20 athletes. Okay, and we'll just hit OK. Aha. This is much better. Much, much better. Why? Because it's telling us everything. It's reminding us the confidence level is 99. It's telling us the degrees of freedom are 19. It's like we can verify. So, if one was to do this by hand, it would be x bar plus or minus t sub alpha over 2 with a certain degrees of freedom, which is 19, little s over root n. So, but, that's if we were doing it by hand. Now we see, okay, it's telling us our bounds, so 56.8 to 62.75. Okay? So this is the one I prefer. Okay? In fact, if I go back and look at the other one, I'm thinking it didn't match up, so I'm thinking it may have been a z. 56.8 to, yeah, it's rounded, yeah. But it doesn't give any details, so it's safer to use this. Okay. Okay, so now I've gone back. You've got your confidence interval. You guys all know how to make a statement about mu now. Something like, we are 99% confident that the true population mean heart rate of all the male athletes reside within such and such a bounds. So, okay, now let's take a look at the next problem. Okay, so for number 3, I'll read it to you. It says, suppose you're interested in estimating the average salary for biostatisticians in Connecticut, and you obtain a random sample of 25 biostatisticians hired in the last 5 years, and the sample data appeared to be approximately normally distributed with no outliers. So, I mean, right there you go. That's sort of giving us the assumptions to use T procedures right there. The average salary for the sample is $45,000 with a sample standard dev of $31.50. Construct a 95% confidence interval for mu, the true average salary for newly hired biostatisticians in Connecticut. Okay, keep those big numbers in mind. N equals 25, sample means $45,000, standard dev is $31.50. And let's go ahead and run that interval. If we have summary statistics like that, you can just go ahead and run it pretty easily. Megastat, confidence intervals, as you saw earlier. Now see, if I don't pull, I'm just going to highlight this last sentence here. I like to have it in front of me when I'm on Excel. X that out. Okay, I'll try that again. confidence interval. So I know that n was 25, less than 30. That's why we had to have those assumptions stated to use the t procedures, small sample size. So the central limit theorem doesn't kick in. We don't really see that kick in until n is bigger than 30. 95% confidence, sample standard dev 3150, sample mean 45,000. Okay, and we'll go ahead and hit OK. So you see the bounds. I'll let you retrieve the bounds from there. It's like 43,000, close to 700 bucks. In between 43.7 and 46.3, 46,300 for the lower and upper bound. So you can make a sentence about that. We are 95% confident. I'll let you fill in the blanks there. Okay, but it says how large of a sample is needed to estimate the mean to within $2,000. Well, currently, let's talk about the margin of error. When you say within $2,000, that's the desired margin of error. So to be within 2,000, well, the current margin of error, I'm just going to write that here, the current margin of error is the half width, which is 1,300. So we say, okay, if I give you a little more wiggle room and say I need the estimate to be within 2,000, how large of a sample is needed? Well, remember that that is a calculation in and of itself that we learned in class, but we also remember that Megastat makes that really easy to do. So we go to Megastat. Back to confidence intervals, but sample size mean. That means sample size needed to estimate a mean with a desired margin of error, which we said is 2,000. And standard dev, we don't know the population standard dev, but we have an estimate based off of our sample. Okay? And now, when your sample size is small like that, though, you're not supposed to use the sample standard dev as an unbiased estimator for population standard dev. I'm just doing that for this calculation. Confidence level, we're going to keep at 95 and hit OK. Aha! 10. So notice that the answer is 10. Well, if you think about it, this makes intuitive sense. 10 is smaller than 20. And you say, well, you want to be less reliable, you can sample less people, right? So in other words, we made the margin of error larger. We said, all right, you don't need it to be within 1,300. What if we needed it only to be within 2,000 bucks? Well, there you've let the desired margin of error be larger, so you can poll less people. Basically, you can sample less people. Okay. And you know, if I wanted to shrink the margin of error, what would I have to do? I'd have to poll more people. So sample size would go up. So in fact, you know, let's just play with that. What if I wanted it to be within 500 bucks in terms of accuracy? Because originally it was within $1,300 was the margin of error. So sample size. Okay, now I want it to be within 500 bucks. We'll keep those same information. Okay, 150, then I'd have to poll 153 people. So that's interesting, because there I shrank the margin of error from 1,300 some to 500 bucks. And I'd have to poll a lot more people. So again, I wanted to highlight that original margin of error, and I like that Megastat keeps everything on track there. That original half width or margin of error was 1,300. So here's the 1,300 margin of error. And, you know, we had to survey 25 people. Okay? Then, if we wanted to make the margin of error, the error tolerance 2,000, we'd only have to survey 10 people. But then, if we wanted to make the error tolerance 500, we'd have to survey a lot more people. So that should make intuitive sense. Okay, let's take a look at the next one. Well, in fact, this is our last one. Some say Hillary Clinton is unstoppable for 2016. A recent poll indicates that 586 out of 1,000 voters will favor her in the next election. So we're assuming that's a random sample, perhaps even a cluster sample of the United States. Create a 90% confidence interval for P, the true population proportion that will favor her, and interpret. Well, so based off of that one little point estimate, now, interesting here, I wanted to mention, I didn't ask it, but what assumptions are needed in order to do this, in order to run this confidence interval? Well, remember that n times p times q is supposed to be greater than or equal to 10 in order for us to use z procedures, which we're going to use here in a moment. So p is your point estimate for your population proportion. So 586 out of 1,000, it's like 0.586. And multiply by 1 minus 0.586 is, and then multiply that by n, your sample size. And if you get a number greater than 10, we feel that you've polled enough people to do this. They let the central limit theorem kick in. Okay, so we're going to create a 90% confidence interval for P, the population proportion. And just remember that magical number, 586 out of 1,000. Okay. So I'm going to go to Megastat, confidence intervals, P. So make sure you highlight this one that says confidence interval P for the population proportion. Little p is your sample proportion, which was 586 out of 1,000. N is the number you polled or surveyed or sampled, 1,000. And how confident did we want to be? I already forgot. 90% confident. Okay. 90% confident, and go ahead and hit OK. Like I said, I'm assuming that you're going to be retrieve all this information and copy paste it into Word so I see that your output. So the bounds, you can make a sentence. So I see the bounds here are between 56 and 61%. So we believe that and we're fairly confident, 90% confident, we believe that between 56% and 61% will favor her. Now notice that entire interval is above 50%. So it's pretty strong evidence that she will win. Okay. After we created that interval, and then it says based off of that interval, is there strong evidence to say she will win? So yes, kind of gave that away. And then in part C, it says how large of a sample is needed for a desired margin of error of 2% using the 90% confidence and the point estimate that we just had. So let's take a look here. Desired margin of error 2%. Let's just take a look. Well, this is kind of interesting. Remember that the Megastat half width 0.026, that's the current margin of error. So you say, well, what if I want to shrink it to 2%? How many people would I have to poll? So in other words, we currently if n equaled 1,000, we got this, we had 2.6% basically margin of error, which isn't much more than 2%, but you say, what if you want to shrink it to 2%? How many more people would you have to poll basically? Okay, well again, Megastat makes that real easy. Megastat, go down to confidence intervals, go down to sample size P. So that's sample size to estimate a population proportion with a desired margin of error, with an error tolerance, 2%. So we're going to key in 0.02. Little p is our point estimate. By the way, if you don't have a point estimate, use 0.5. But we do, so we'll say 0.586. Okay. We'll keep confidence at 90, and we'll hit OK. Wow, 1641. 1641. So just to shrink that margin of error a little bit, so many more people would have to be polled, right? And you say, is it worth it? And there's where you get into time and money discussions. Is it worth it just to shrink it, the margin of error, that little bitty amount? Okay? All right, let's double check the Word document, make sure we have everything. And that's it. All right, good luck with fine-tuning that. Hope that helped.